Okay, so up to this point, we have talked about light as if it were rays that travel in straight lines, um, and that which we can perfectly determine the direction in which they'll travel given their starting direction and knowing the properties of the lenses they're traveling through, right? But this is not a complete picture of the nature of light, right? Um, Light is also a wave. And because it is a wave, in addition to a particle, it can do things like interfere with itself constructively and destructively. So for example, let's say, um, right, if we want an example of two waves that are perfectly destructively interfering, we can draw one wave, and then if we start another, but we're going in the opposite direction, obviously these are perfectly canceling each other out. And if these were um, two different paths that a photon could take, it would cancel itself out, and we'd have a dark spot wherever these two waves were going, right? What's interesting is that we can also have multiple frequencies in a system. So we might start out, let's do blue again, we might start out, so there's blue and then red. Let's say red is a slightly higher frequency, so a shorter wavelength. We might start out with destructive interference, but then end up with constructive interference, right? Or constructive interference, you've done this in physics class. Constructive interference is where the waves line up and coincide with each other. So these two phenomenon, where we can have multiple frequencies, but also multiple distances, right? If we were, for example, to move the start of this red wave, this red wave over to here, if we move the start up to here, right, then these waves would be coherent the whole way. And that corresponds to something we might call spatial coherence, and another one, and also temporal coherence. So this is temporal coherence, where we have different frequencies involved, and we also have spatial coherence, which talks about the distances that the two different rays might travel. So, like I said, light travels like a ray, but it is a wave. So we need two ways to talk about how similar two rays of light can be that are passing through our system. So with temporal coherence, this is a very specific definition. What it says is that looking at a single point in space, so this might be a point on a camera sensor or something like that, right? How long, oops, are two beams in sync, right? And what in sync is varies in definition, but it could be the time that waves differ by less than 50%. So what that looks like is, let's skip this comment here for a little bit and move on to the next page. What this looks like is, for example, two waves might differ because of a variation in frequency. So this is a variation in frequency. And if you've ever heard two notes being played by people that are slightly out of tune, you'll notice that there's a beat pattern with the sound, right? You actually go down, and that beat pattern is the way the sound waves coming into and out of constructive and destructive interference. And the half the time it takes to go from destructive to completely constructive interference is a time constant, essentially, right? And that is the this is the temporal coherence, right? Temporal coherence. In addition to seeing this described as time, you might actually see this described as a distance, because remember, with light, time and distance are absolutely related. The speed of light is equal to the wavelength times the frequency, right? So we know the speed of light is fixed. So if you know one, you know the other. So a variation in frequency is also a variation in wavelength. What you might see is somebody that they might post a graph that shows for a light source a distribution of wavelengths, and they might give you the half width of this peak as the temporal coherence, right? And this might give you like 5 nanometers, which is actually a decent temporal coherence, right? Good lasers will have much smaller than that. LEDs will be larger than that, right? Incandescent sources can be quite a bit larger. So temporal coherence, right? Emitting multiple wavelengths, and these wavelengths can interfere with each other. You can also have temporal coherence, incoherence or coherence, if you have waves that are the same frequency but leaving at different times. So they can have a constant phase difference, or basically. So let's say we have our red wave and we also have our blue wave, right? See if I can draw. It's actually kind of difficult to draw two waves just out of sync of each other. So these two waves have a constant phase difference, right? So you might have a range of photons leaving that are leaving at different times, and as a result, they have a difference in phase, and so that they might partially interfere with each other. So it's important to note you might have a combination of these. For example, with an incandescent lamp, photons are leaving at random times and at random frequencies. Whereas with a laser, you have a very narrow range of frequencies that your photons are leaving at, and they are typically in very nearly in sync because of the way that lasers work, right? They are, a photon comes in, stimulates the emission of another photon. Because of the way that that photon is stimulated to emit, it is emitted at the same phase as the photon that created it. So you end up with this cascade of photons that all have the same phase. And some lasers have multiple of these events going on. So you might have groups of different phases that are emitted, and some lasers, which are very more expensive, have a single phase that is emitted because you start with a single photon, or they're good at selecting single photon events and then growing them so that all the photons that leave are in phase. So yeah, the same frequency but leaving at different times is for very, how do I put this? This is for very rigorous applications, if you will. The variation frequency is a much more common application of this, where you might look at a laser or an LED and get an idea of the temporal coherence of that light source, which tells you the range of frequencies that are emitted, right? Cool. Spatial coherence is a different beast, right? For spatial coherence, it says for a given wavefront, for us today, for a given source, how far can you travel before wavefronts stop interfering when averaged, oh my gosh, averaged over time, right? Cool, so let's look at how that looks on the next page. Let's say we have a point source, right? An absolute infinitesimally small point source of light. And then we were to look at the wavefronts that exist after it passes through a perfect lens, right? So the wavefronts from this point source are the basically, remember, wavefronts are the lines that connect all the rays perpendicularly, but they also happen to be the lines of equidistance from that point source. So we have wavefronts that travel spherically coming from this point source. They hit our lens, and then they start traveling as parallel waves, right? And so what we find out is that all of the photons that leave this point source, when they get to this wavefront, or let's draw a wavefront right here that goes through our red, our orange. When they get to this wavefront, they have traveled the same distance, all of them. So you notice the lens is thicker here as we get to the middle. It also has a higher index of refraction than air. So the effective distance it has traveled is the same. So all of these rays have traveled the same distance. And as a result, right, they, if we were to measure a pattern of interference, it would not be averaged out. Now let's talk about what it means to be averaged out. Let's say we have an incandescent light source, right? That means you have a finite size. This is an infinitely small light source here, right? You have a finite sized light source. Light is emitted from the top, from the middle, from the bottom, right? And each one of these is going to produce a different set of wavefronts. So you're going to get from the top here, you're going to get, let's do these in different colors actually. So green, you're going to get, I'm going to exaggerate this, right? You get spherical wavefronts settled around that one, but then they're also at an angle when they leave the lens, like this, right? So that was blue. If we do green now, then the middle, we get balanced wave fronts coming out, and then straight up and down wave fronts leaving here. And finally, from the bottom, if we call that, let's call that purple, if you will. Purple, we're going to get wave fronts coming from the bottom that are centered on that one, but again, when they leave the lens, they're going to be angled like this, kind of angled traveling upwards. So the result is, I mean, here we've only drawn three lenses or three rays, but there's an infinite number of points on this incandescent light source. And so if we drew an infinite number of lines here, all you would see would be a mess, right? And as a result, this one has a very low spatial coherence. Very low spatial coherence, on the order of nanometers, right? It's very low. Meanwhile, this has a very high spatial coherence, on the order of meters or kilometers. I mean, very high spatial coherence can be on the order of meters. Getting to the point of kilometers is difficult. So that's what spatial coherence means. It means, given a certain point in space here, right, how different is the path length of all the different rays that can pass through it? So if we want to draw those rays now, let's draw those rays that are coming through here, basically. So here we have blue coming through, we have green coming through, and we have purple coming through. And you'll see that the path length for each of these rays is different, right? Purple took the shortest route, blue took the longest route. And as a result, we talked about this up here, right? Since their path is different, they're offset by a constant phase difference. But since we have an infinite number of these points, there's an infinite number of phase differences. And so there's no coherent pattern. It's you literally, for every single point that might be constructively interfering with another point, there's another point on this incandescent lamp that is destructively interfering with it. So you just can't see anything. And the result is what we see from most of our light sources in our life, which is a nice even light, right? Um, the With a point source like this, you'll see lots of interference fringes and things like that that are not an um, even source of light, because you are able to see these constructive and destructive interferences very easily. Great. So why lasers are incredibly useful. Because they are to varying degrees, right? Some lasers are less coherent and some are more coherent, but they are spatially and temporally coherent. Okay. So why does, let's ignore that. Why does coherence matter? Well, let's pause for a second here. Now that I'm thinking about it, the reason why lasers are spatially and temporally coherent is because if you have a laser, the light that leaves that laser usually leaves as close to a parallel beam as you can get. So the wave fronts are all perpendicular to the beam direction. Now, this isn't quite true because diffraction is going to cause them to spread out a little bit, but it's fairly true. And all of the light is very close to a single wavelength, right? So the end result is you have as close of an approximation as you can get to a light coming from a single point source like we had above, but one that is infinitely far away. Because an infinite point source, one that's infinitely far away, the radius of curvature of these lines is going to be infinite, which means they're straight, basically, right? So we have an infinite point source that is located infinitely far away that is emitting a single wavelength. This means it's both spatially and temporally coherent, which is fine by itself. But lasers are great because we're able to actually put a decent amount of power into that beam. It used to be that when people wanted to do this, so for example, people needed spatial and temporal coherence long before lasers were invented. What they would do is they would take a candle. Oh, that kind of looks like a flame. They would take a candle, which is emitting all kinds of light in all directions at all different frequencies. And what they would do is they would, first of all, put a filter in front of it that maybe absorbed everything but the blue light. And so what comes out is mostly just blue light, right? So blue's coming out, yellow's coming out, red's coming out of this candle. And then after going through the filter, blue comes out mostly, but it's still coming out in all directions with a lot of different wavefronts. And so what they'll do is they will take a lens like this, and they will focus it down and put that light through a pinhole. They'll have another lens coming out here. And so what happens is let's say we have a wavefront that's traveling parallel to this lens. That wavefront is going to be focused down right to this pinhole, and it's going to make it through. And it gets through, and it comes out parallel again, and we have nice, beautiful wavefronts like that. But a wavefront that is maybe traveling at a different angle, right? That wavefront is going to be focused up here, and it's not going to make it to that pinhole. So only wavefronts that are who are traveling perpendicular to the lens are going to make it to this pinhole. Curved wavefronts like this, curved wavefronts, part of it will make it through that hole, but not very much, because a curved wavefront, if it looks like this, basically is going to be focused at a point way back here, which means only a little bit of it will make it through this hole. And so by putting this pinhole here, what we're doing is we're selectively choosing as much as we can wavefronts that are only parallel parallel to the lens or perpendicular to the beam path. And so that's how we get spatial coherence and to a small degree temporal coherence. It was hard to get good temporal coherence before before some really advanced lens coatings that we have now, which are really good at selecting wavelengths. So that's how you would do it. But if you'll notice, right, most of the light is being blocked by this pinhole. Most of the light is focused to points other than the hole itself. So it does not make it through here, and as a result, you're losing 99% of your light, right? So pinholes are an inefficient way of producing spatially coherent light, whereas lasers are a very efficient way of producing it. So that's why we love lasers. All right. In our next video, we're going to talk about why this spatial and temporal coherence is useful by mostly talking about the double slit experiment.